There's a lot going on here today at the zoo, and I can observe it all through my ears. But how do my ears pick up on a monkey or an elephant? And why are they so different? Let's find out together in this episode all about sound. Can you hear that? Every sound you can think of is made the same way, through vibrations. When something vibrates, it oscillates up and down or back and forth really fast. When we speak or sing, our vocal cords move and vibrate, creating sound. You can feel these vibrations by gently resting your hand on the front of your neck. Hello, 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 hello. See? The air all around us is made of particles. These particles are actually what carry sound. When an object like this tuning fork vibrates, it causes movement in the surrounding air particles. These particles bump into other particles that are close to them, which makes them vibrate too. And this process continues, spreading outward until the particles run out of energy. Sound always starts with some kind of mechanical movement, a tuning fork, or a ukulele, or even a glass of water. These movements cause some vibrations in the molecules of the tuning fork, the ukulele, or a glass of water, which starts that transfer of movement, or vibrations like we just mentioned. These vibrations can travel through 3 states of matter: solids, liquids, and gases. The more densely packed the particles are, the faster the sound travels, which is why sound travels faster in solids than liquids and slowest of all in gases, and not at all in a vacuum like space. This is because there are absolutely no particles for the sound to vibrate through. A sound wave is the pattern of disturbance caused by the movement of energy, or vibrations, traveling through a solid, liquid, or gas as it speeds away from the source of the sound. So if you're close enough to an object's vibrations, the sound waves that are created will reach your ear. But not all sound waves are the same. Sound waves are a type of longitudinal wave that travels as a series of compressions and rarefactions. Compressions are the areas where the vibrating particles are closest together, and the rarefactions are the areas in between, where the particles are spread out. Also, because sound changes speed as it moves from one medium to another, means it can be reflected, refracted, and absorbed just like light can. Hard, flat surfaces are what reflect sound the most, which is what give us echoes. Echo, echo, echo. If you're still here liking this video, let us know. And hit that subscribe button so you never miss an episode. This is all really great, but how can we interpret these vibrations in sound waves to register that this elephant isn't this monkey? How do we hear those vibrations? Let's take a look at the human ear. This is what the inside of the human ear looks like. Here is the ear canal, the eardrum, the ossicles, which are a group of 3 small bones, the cochlea, which looks a bit like a shell, and the auditory nerve. Whenever sound waves reach your ear, they travel along the ear canal and hit our eardrum, which causes it to vibrate. These vibrations then are transmitted along the tiny bones, called ossicles, through the semicircular canals, and into the cochlea. The cochlea then converts the vibrations into electrical signals. These signals get sent along the auditory nerve to your brain. Your brain is then able to amazingly interpret those signals as sounds, but not all sounds are the same. When there are more sound waves passing through a fixed place at a given time, the frequency is high. When the number of waves becomes less, we hear low frequency sound waves. So air that's vibrating back and forth more times per second will have a higher frequency, and air that's vibrating fewer times per second will have a lower frequency. Humans hear sounds best when the vibrations are somewhere between 20 per second on the low end and 20,000 per second on the high end. Any frequency above or below that is inaudible to the human ear. Higher frequency sound waves will give us a higher pitch. As we age and lose more of the cells that help us detect sound, we start to lose the ability to hear higher pitched sounds. But some sounds are too high or too low for any human to hear to begin with. Sounds that are too high pitch are ultrasonic sounds, and sounds that are too low pitch are infrasonic sounds. Dog whistles, for example, use an ultrasonic pitch that is too high for us to hear. Elephants use infrasound, or sounds below the range of human hearing, to communicate long distances. These low-frequency sounds can travel several miles. Scientists are still learning so much from studying how elephants use these rumblings, but so far, it looks like they use these sounds to find family members, court potential mates, and for warnings. Birds also use infrasound to detect approaching storms, sometimes hundreds of miles away. Loudness is another aspect of sound. When you increase the intensity of a sound, you increase its loudness. Decrease intensity, decrease loudness. Intensity is just another way of saying power. As sounds get closer or move farther away, the intensity changes. The closer to the source of the sound, whatever is causing those initial vibrations, the greater the intensity of the wave that hits your ears. Let's use this speaker to help us visualize intensity. Our speaker from the zoo is now inside of this metal bowl. On top, we have stretched out some press and seal wrap, and we have some rice that we are going to place on top. This is going to allow us to observe the different intensities of the sound waves that we've collected from different animals. The more intense the sound, the more the rice will vibrate. That was amazing. So many interesting sounds out here. Pay extra attention to the frequency and intensity of the sounds around you today. And if you want to learn more science, you can check out this video next. The ukulele, the ukulele, the ukulele.